Good afternoon, everybody. I don't know. Maruti Gaud seems to be always having a problem entering the class. I am under the assumption that he has been trying to enter the class using some Gmail account. But he says he's coming from IFHE only. See, outside IFHE, not allowing. I don't know what's happening. Okay, so let's just start the class. So in the last class, we have seen how a moving charge can actually be the source of a magnetic field. And we've seen the equation for the magnetic field. The equation is B is equal to KQV cross R by R square. So that's what we have seen. Or the magnetic field is perpendicular to the path of the moving electron, and the magnetic field forms closed cycle, and it is inversely proportional to 1 by r square, where r is the position vector of the point with respect to the moving charge. Now, with these things in mind, let us just go ahead and look at the next stage. The next thing, and then before that, I also want to tell you that this preparation or getting a magnetic field using a moving charge will not work in real life, because the magnetic field that you will produce will be very small. How do you know it's very small? We know it's very small because we did a problem last class. We have seen that the magnetic field is of the order of 10 to the power of minus 16 Tesla, which is very small. No Gauss meter on Earth can measure that. Does it mean that this entire exercise is a useless exercise? No, it is not. We have also seen that when R becomes very, very small, like what happens inside an atom, if you're talking about interactions of subatomic particles, there the magnetic field that each can set up becomes so significant that the magnetic properties of materials will be decided by this particular equation. Now, once we're done with this, let's just go ahead and talk about the magnetic field due to a current. Let's look at magnetic field due to a current. So when we are talking of magnetic field due to a current, it's just an extension of what we have done in the last class. A current is, after all, a series of charges which are in motion. So what we'll now do is we will take a conductor. Okay, so here is a picture. This is a conductor carrying a current I. And let this conductor be lying on this plane that is shown in the picture. Okay, and I want to find out what is the magnetic field because of this current carrying conductor at a point P. So now, just as what we did in chapter number 25 and 26, here we are going to imagine this conductor to be made up of a number of small segments. Okay? And even before that, I want you to recall something. So what is it? We have seen that the magnetic force, that is previous chapter, magnetic force on a moving charge is given by QV cross B. Okay, then the same chapter we have seen how instead of a moving charge, if you just had a wire, the equation simply becomes FB is equal to integral I dl cross B, where dl is the length element carrying a charge dq. Or you can see that QV translates into I dl. Q is charge, I is current. Okay, now this same relationship, what we are going to use in this particular chapter also. So instead, we already know what is the equation for a magnetic field because of a single charge. Okay, so let's see how this idea is going to be used. So we consider this current element to be made up of small segments of length. Somebody is constantly messaging. Who is this? I don't know what's the problem. Classes are just getting disturbed. If I'm going to cater to one person's requirement, can someone just help that guy, tell him where he may be going wrong? Maruti Gaud. He is on the group or WhatsApp.
Ma'am,
Okay.
actually, he is unable to join through IFHE email ID.
What is actually the problem? I don't know. But now I'm not able to even see him trying to come in. I'm not even able to see that. Even if I want to help him, no. First, I denied him permission because I thought he was coming from Gmail. But now he's not even appearing. Okay, so let's continue. So we will take a small length element of this long current carrying conductor. Let the length of this be some ds. Okay, you can see the small piece. Let the length be some ds. And ds can be treated as a vector by drawing a tangent. If I draw a tangent, this arrow gives me the length of, the direction of the ds vector. And I'm interested in finding the magnetic field at a point P. So the position vector of this point with respect to, the position vector of the point with respect to the charge is going to be vector r. And the angle between ds and r is going to be phi. And let the magnetic field because of this small length element be dB. So dB is going to be mu naught by 4 pi dq v cross r by r square. V cross r cap by r square. What is dq? dq is the charge in that small element which is moving. The small element dq that is moving along that length ds. So now what we're going to do is this dq into v vector, we are just going to substitute with I into ds. dq into the v vector, we are going to just substitute with I into ds. How are we doing that? By just look at the recall equation where q into v vector was written as I into dl vector. Same logic we are going to take and then make this substitution. Okay, so this is the magnetic field at the point P because of that current in the small length element ds. What will be the direction of dB? Direction of dB is given by the direction of the cross product of V cross R. The direction of the cross product of V cross R. Now, what will that be? Let us see. You can see that if this is the direction in which the charge is moving, this is the direction of the velocity vector also. So the angle between the velocity vector and the r vector is phi. Okay, so instead of qv cross r, we are going to write I ds cross r. So again, I repeat, it is coming from here. This is the logic. Okay, and what is going to be the direction of this? The direction of this is going to be given by the right hand rule. So it is V cross R direction. So V cross R direction, you're seeing that dB is down. It is down and perpendicular to the plane that is given to you there. Now I want the magnetic field due to the entire wire. So what do? I have to take all such elements. I have to take all such elements starting from here all the way. Or in other words, I will take all such elements, get the magnetic field because of each of these elements and then add them up. This adding up becomes an integral. So when you do an integration of dB, you're going to get mu naught by 4 pi into integral I ds cross r cap by r square. Okay, and this ds cross r cap is simply going to be equal to ds sine phi because r cap is having a magnitude 1. Okay, so look at the expression that we have written in the box below. So it is going to be b is equal to mu naught by 4 pi integral I ds sine phi by r square. So this is your Biot-Savart's law. Okay. Now what we'll do is we have seen for a general current carrying wire. Now we will see different geometries, different configurations of current. So this is similar to what we have done in the chapter 25 and 26. In 26, we found out the electric field due to some charge. Then we found out the electric field due to a line charge, then a ring, then a disk. Okay, similarly here also we are going to find out the magnetic field due to a straight line conductor, then a ring. Okay, let us see what else we'll be seeing here. So the first thing is going to be the magnetic field due to a straight wire conductor carrying a current. Okay, so here is your straight wire carrying the current. straight wire carrying the current. Let L be the length of this wire, and the wire is lying along the z-axis. It is lying along the z-axis. It is lying between, let us say, minus L by 2 to plus L by 2. So the center of this wire is at the origin. So this is your XY coordinate system. This is X axis. This is your Y axis. This is your Z axis. I'm interested in finding out what is the magnetic field at a point P on the perpendicular bisector at a distance D. Okay, so from here, we consider a distance D, take a point P, find out what is the magnetic field at that point because of this entire wire. So as we normally do, take a small length element. So this is a small length element that we have. And this length element is going to have a distance or length dz. It has got a length dz. And where is it located? It is located at a distance z from the origin. At a distance z from the origin. And what is the magnetic field because of this dz element at the point P? So for that, first of all, draw your R vector. Okay. And then you have to find out what is going to be the magnetic field. And first of all, go back to this equation. dB is equal to mu naught I ds cross r cap by r square. Let us find the analogy here. What are all the elements here? So mu naught I by 4 pi remains as it is. Okay. And instead of ds, you're going to have dz. Instead of ds, you're going to have dz cross r by, here, r square in the original equation is the distance between the point P and the charge element. But when we write r square here, we just take this right angle triangle, and then you can write your r square as z square plus d square. Z square plus d square. So that's why you're getting this. Okay. Now we need to get rid of this r cap. So let's do the cross product. So this becomes mu naught I by 4 pi dz sine phi by z square plus d square. Why sine phi? Because it's a cross product and phi is the angle between dz and r cap. This is your angle. This is phi. This is the angle between your dz vector and your r vector. Okay, so that's your phi angle. Okay, now what you do is, let us try to write what is phi. It's already written, so let me not waste time. Okay, it's just trigonometry. Trigonometry will tell you that sine phi is also equal to sine of pi minus phi. Sine phi is also equal to sine of pi minus phi, which from this right angle triangle becomes d by under root of z square plus d square. So we are going to substitute this in place of sine z. So when we make the substitution, you're going to get mu naught I by 4 pi d dz divided by z square plus d square to the power of 3 by 2. 3 by 2 becomes, you are getting, because already here it is 2 by 2, then here it is 1 by 2. So 1 by 2 plus 2 by 2 becomes 3 by 2. So this is your expression for the magnetic field at the point P because of this small element dz, current element dz. Now I want for the entire wire. And now look at the direction of the magnetic field. It should be perpendicular to the r vector and your dz vector. R vector and dz vector. What is r vector and dz vector? It is lying on the yz plane. Both these vectors are lying on the yz plane. Therefore, your b vector, use your cross product and see, or use your right angle rule and see, you're going to find that, okay, dz cross r is going to go into the plane of this sheet. It's going to go into the plane or into the yz plane. Into the yz plane means it is the x-axis with a negative sign. Okay, now let's do the integration. Okay, let's do the integration now. We want for the entire wire. So doing an integration, we are getting mu naught I d by 4 pi. D is a constant, please remember, because d is simply the distance between point P and your wire. So this is your D. So D is a constant. So D comes out of the integral. 4 pi also comes out of the integral. The rest of it, you will do an integration from minus L by 2 to plus L by 2. Z is the variable. Z is going to be the variable. So when you do this integration, okay, without substituting the limits, minus L by 2 to plus L by 2, you're going to get this. Then after substituting the limits, you see what you're getting. Mu naught I by 4 pi d L by L square by 4 plus d square under root. Okay. So this is finally the magnetic field because of a current carrying wire. And we have seen it at this point P, at the point P. Okay. Now, if I take any other point at the same distance D, if I take any other point, I'm going to get the same value only. Or in other words, I find that if I have a current carrying conductor and the current is in this direction, then I have to use my right hand rule, put my thumb in the direction of the current, look at the direction of the curling finger. The curling fingers are forming circles, and this gives me the direction of the magnetic field. Or in other words, we can use the right hand rule. Now, here we have taken a short wire and we have done this exercise. Instead of a short wire, what if I take a long wire? What if I take a long wire or take my point P such that my D is much less than L. I take a long wire, or alternately, I take a point very close to the wire. Then all I will get is D much less than L, or L much greater than D. When I do that, let's see what happens here. Okay, so it's just one step. B will be equal to mu naught I by 4 pi D L divided by, let us take L outside. If I take my L outside with a square, L square outside with that under root, it becomes L. Then I get 1 by 4 plus D by D square by L square. Okay. And this entire thing is going to be half. And what happens to D square by L square? If D square itself is much less than L, D itself is much less than L, D square will be much less than L. Or in other words, this can be neglected. Okay, then this L and L will cancel out. And then 1 by 4 root will become half. This half, when you're going to put it into this, 2 will go to the top. Okay, or I will write one more step. It becomes mu naught I by 4 pi D into 2. Okay, under root of 1 by 4 is half. So this half in the denominator will become 2 in the numerator. So this 2 and this 4 will give you this. That's how you end up getting mu naught I by 2 pi D. I'm sure this is an expression you have all studied. So for a long current carrying wire, if the current is I, at a distance of D from the wire, you're going to get a magnetic field mu naught I by 2 pi D. Here the assumption is that D is much smaller than the length of the current carrying straight wire. And the direction is given by right hand rule. Okay. Now, what is the other thing that comes out from here? You're also able to see that B is inversely proportional to D, or B is directly proportional to 1 by D. As you move away, as point P moves away from the wire, you're going to get smaller and smaller values of magnetic field. However, magnetic field will be giving circular loops. Okay. Now, at this point, from an examination point of view, what I would want the students to normally do is make a comparison between an analogy of this in chapter number 26. In 26, we had a conductor, a line conductor. Sorry, it was an insulator, a line with uniform charge, which is not moving. What is the magnet? What is the electric field on the perpendicular bisector at a point P? You got an equation which more or less resembled this. Okay. Next, let us look at the magnetic. Another geometry we are going to see is the magnetic field due to a circular loop of current. So here what we do is, this is our circular loop. Okay, so this is our circular loop of radius r. And C is the center of the circle. And the direction of the current you can see is this. I is the current. You're going to take the axis. Axis is lying along z-axis, let us say. And let's say that the center of the circular loop is the origin. And this is your z-axis. Now on the z-axis, that is on the axis of the circle, at a point P, which is at a distance z, you want to find out what is the magnetic field. So as usual, take a small length element. Take a small length element. The direction of that length element is this. That is the direction of the current. And this vector, we call it as ds. Okay. Now, what is the magnetic field at the point P because of ds? So the next thing we define is going to be our r vector. R vector is the position vector of the point P with ds as the origin. Next, what is the angle between them? What is phi is the next question. You can see that phi will be 90 degrees. Phi will be 90 degrees. Okay. Now, next thing you want to know is, let the magnetic field that it sets up at the point P be dB. What is the direction of dB? We have to see. dB will be perpendicular to, dB vector will be perpendicular to r vector, and it will be perpendicular to ds vector. And a little bit of common sense, you can actually see that what you have is going to look like an inverted cone, and you're going to draw a perpendicular like this. So this perpendicular is not going to be on the xy plane. This perpendicular, I'm sorry, this dB vector that you're drawing is not going to be on the xy plane. Instead, it will be making an angle alpha with the z-axis. It's going to make an angle alpha with the z-axis. Okay. Next, what you do is, let us write what is this dB. dB is mu naught I by 4 pi I ds cross r by r square. Then ds cross r cap, we can write it as ds sine phi, which is equal to ds as phi is equal to 90. Okay, so that's how you're getting this. Next, what you do is simplify it and write. Instead of small r square, you can see that it is going to be small r square is going to be from this right angle triangle, it's going to be capital R square plus z square. So substitute that also here. So you got the expression for dB. And we saw how this dB is going to look with respect to the z-axis. It's going to make some angle alpha. Alpha is not 90. Please mind it, alpha is not 90 because you are having some kind of a conical structure and a perpendicular to the conical structure. So it cannot be 90. Next, what we'll do is, we have to take a similar element, a mirror image element we have to take. This is our ds now. Okay. Then next what you do is, you have to take a r vector. You have to take an r vector. This is going to be your r vector. And you have to get a dB for this. Let me use some other pen color for that. If I get the dB because of this mirror element, I'm going to get dB like this. Okay. And I will see that dB is again, this dB is going to make an angle alpha. Okay. Or in other words, because of two elements which are diametrically opposite to each other, I'm going to get two dBs like this. I'm going to get two dB vectors with same magnitude, but which are going to be like this. I'm making an angle alpha with the z-axis. Going to make an angle alpha with the z-axis will be two vectors dB and dB. Okay. Now what we'll do is, let us try to add these two. I will add two vectors like this, dB and a vector dB, making an angle alpha with the z-axis. Okay, when you try to do this, you can actually draw the components and see, this is one component, this will be another component, these two components will cancel out. And there will be one component along the z-axis for the first vector, another component along z-axis for the second vector. Or in other words, these fellows will survive. They will survive because they are parallel to each other, whereas these guys will be lost. These guys will be lost because they are opposite in direction to each other. They will cancel out. So let's see which is the component which is going to survive. Let's write mathematically and see that this fellow is going to survive. So here is your right angle triangle. This is your alpha. So this guy is going to be dB cos alpha. Now dB cos alpha will come from two such triangles. From two such triangles, you're going to get dB cos alpha. Okay, so you can say that the net field is going to be along the z-axis, and it will be 2 dBz. There will be two such dB cos alphas. Okay, so what you have to actually do here is you have to, if you cos alpha, so it's going to be R. Okay, so this is perpendicular component of field is dB is equal to dB sin alpha. Perpendicular component would cancel out. Therefore, dB is equal to dB cos alpha. Please, there's a mistake here. Okay, cos alpha would survive. Okay, I hope I'm right. Yeah, base is going to, so it's cos alpha. Cos alpha would survive. So you can actually write the equation for cos alpha. How do you write cos alpha? Cos alpha, you have to write it in terms of this right angle triangle. Look at this. You can see that if this angle is alpha, this angle is alpha. Okay, so cos alpha is going to be R divided by small r, which is R divided by capital R square plus Z square under root. Okay, so that's the substitution you're going to make here instead of cos alpha. And here in this, you won't see 2 mentioned there. He doesn't mention 2 because he's going to take all such elements for the net field at the point P. He's going to take all such diametrically opposite elements, or you have to come around the circle once. But if I take 2 elements like this and do it, I don't have to come around the circle once. I have to come around the circle just half of the circle. If I come, that's sufficient. Okay. So therefore, do an integration and your answer is this. Okay, so this is the expression for the magnetic field along the axis of a circular loop of current at a distance z. Next, what we'll do is, what is the direction of the current? Let us see. What is the direction of the current? Let us see. Here also you're going to use a right-hand rule. This right-hand rule is the opposite of what we have done for a straight wire. In the straight wire, my thumb was the direction of the straight wire carrying current, and my right-hand fingers were the direction of the magnetic field. Whereas here it will be the opposite. The current loop, the circular current loop becomes the right-hand fingers, and my thumb gives the direction of the magnetic field. Thumb gives the direction of magnetic field. So that's why the magnetic field, if I have a circular loop of current like this, okay, and if I'm going to take a point at a distance z along the axis, then the magnetic field here is going to be given by this direction. Right-hand rule. Now the analogy for this is going to be a circular loop of charge for electric field. Okay, next, if my loop is going to become very small, what if my loop is going to be, or no, before that, what happens if z is 0? I at z equal to 0. When I say at z equal to 0, I'm talking about a point P here. My point P has come to the center of the circular loop. When it comes to the center of the circular loop, in this equation, wherever z is there, you have to put a 0. That's all. So when you do that, you're going to get mu naught I by 2r. Mu naught I by 2r. Or you're finding that the magnetic field once more is inversely proportional to the distance. Okay. And it is directly proportional to the current. Current is the source and given by right hand rule. Now for a minute, let me just take you to chapter number 25, where you were talking about a charge Q and you were interested in finding out the electric field at a point here. So there you would have found that the electric field is 0 at the center of the charge loop. That's the difference between electric field and magnetic field. In the case of magnetic field, the magnetic field at the center of a current loop is not 0, unlike in the case of electric field due to a loop of charge. Okay, now here we have talked about a circular loop. What if I have a part of a circular loop? What if I have a part of a circular loop? Let's say this is my loop of current. Okay, and let the radius of the loop be some r. The current is I. And you're saying it's not a complete circle. It is not a complete circle. It is just an arc of a circle. It is just an arc of a circle. So what we'll do is, first thing we have to find out how much of the circle is there, which you can get by looking at what is this angle. Okay, just by looking at what is this angle. Let this angle be theta. So what we'll do is, again take Biot-Savart's equation only, take the same equation. And here we are just going to make a small modification. What is ds? ds is an arc length. So we can say that ds is going to be equal to r into d theta. R into d theta. Okay. So instead of ds, ds is a small length element here. So instead of ds, you put r into d theta. Then do an integration. You're seeing that r is a constant, so only theta is going to be the variable in this integration. Only theta becomes a variable. Take everything else out. So you're going to get b equal to mu naught I by pi r integral d theta. When you do this integration, you have to do from theta equal to 0 to some theta equal to theta. So this is the angle. Okay, so you get mu naught I theta divided by 4 pi r. Mu naught I theta divided by 4 pi r. But the most important thing that you should remember here is that theta is in radians. Don't take theta in degrees, theta is in radians. Now, for what if it's a full circle? If it's a full circle, let us just do it and see. If it's a full circle, B will be equal to mu naught I 2 pi. If it's a full circle, the angle subtended is 2 pi divided by 4 pi r. See, let's see what's the result we are getting. Yes, this is correct. This is what we should have got for a full circle. So for part of a circle, the formula that you are given there is the formula. And I'll give you a way to remember that. You can write it as B is equal to, like how I just wrote this down itself, you can see mu naught I by 2r, then some theta part out of 2 pi. Some theta part out of 2 pi. 2 pi is for the full circle, theta is for your part of the segment. So you will, if you write it this way, you can remember better. Now, this is a very important step, what we are going to just now write. We have seen what is a magnetic field because of a circular loop. Now, what happens if Z is much, much greater than R? What is R? R is the radius of the current loop. R is the radius of the current loop. And I'm going to take a point P, which is at a distance Z, such that Z is much, much greater than R. If Z is much, much greater than R, come to the original expression for the magnetic field. And from here, take out Z square. Take out Z square. Z square to the power of 3 by 2 is Z, so it becomes Z cube. And 1 plus R square by Z square. Now, R square by Z square will tend to 0 because Z is much, much greater than R. So here this fellow will go, okay, and you'll be just left with mu naught I R square by 2Z cube. Mu naught I R square by 2Z cube. Or you're going to see that magnetic field is proportional to the cube of the distance. Magnetic field due to a small loop, current loop, is proportional to the cube of the distance. Now these kind of tiny loops where the magnetic field is proportional to the cube of the distance is called a magnetic dipole. This is called a magnetic dipole. Do any of you remember electric dipole? What's an electric dipole? Electric dipole is an entity where you have a positive charge and then a negative charge separated by a distance d, and then you took a point and then found out what is the electric field at this point. We have seen that when Z is much, much greater than d, the electric field that you got was proportional to 1 by d cube. I'm sorry. It is proportional to 1 by Z cube. E was proportional to 1 by Z cube, and this entity was called an electric dipole. Because of that logic, this small loop of current is going to be called a magnetic dipole. It's called a magnetic dipole. This is the source of magnetic field, and the magnetic field is going to fall off as 1 by Z cube. Electric dipole is also a source of electric field, and there also the electric field falls off as cube of distance. Well, after this discussion, now we should ask, where do you find such magnetic dipoles where magnetic field is falling off as 1 by Z cube? Those kind of dipoles you're finding inside your atoms. They are found inside your atoms. So what do you have inside your atoms? Inside your atoms, you have electrons, you have the nucleus. Nucleus is positively charged. It has got all your nucleons. And please remember, the nucleus will spin. A spinning motion is also a motion. So it's a charge in motion. So associated with that, there is an electric dipole. Similarly, your electrons are having two types of motion. One is the spin motion and the other is the orbital motion. Okay, so you have an electric dipole, a magnetic dipole associated with spin motion and the orbital motion of electrons. And similarly, the spin of the nucleus. Now, all these form or give rise to their own magnetic field. And there is interaction between these various elements which are giving rise to magnetic field. And it is this together for an atom which will decide the magnetic dipole values. It will decide the magnetic property of any given material. Okay, now to make sense of what can be the current if an electron is spinning, okay, or if there is an orbital motion, let us work out this particular problem. So we are going with the Bohr model of hydrogen atom. Electron is going around the nucleus in a circular path, and the radius is r. Okay, radius is r. This is your electron. This is your positive nucleus. And the electron is moving around with a radius 3.29 into the power of minus 11 meters. And how is it going around? Let us see. It is moving with a frequency of 6.6 into 10 to the power of 15 hertz. 6.6 into 10 to the power of 15 hertz. That means in 1 second, it is coming around 10 to the power of 15 times. The electron is coming around the nucleus 10 to the power of 15 times. Now the question is, what is the magnetic field at the center of the orbit? Or what is the magnetic field that the nucleus is going to experience? Okay. So what is the equation? The equation is mu naught I by 2R for the magnetic field due to a current loop at the center. The magnetic field at the center of a current loop of radius R and carrying a current I. R value you already know. It is 5.29 into 10 to the power of minus 11. Oh, sorry, I made a mistake here. It is 5.29 into 10 to the power of minus 11 meter. Mu naught is 4 pi into 10 to the power of minus 7 Tesla meter per ampere. So that also you write. What about the current? How do I write current? One single electron is going around. So how do I write it as a current? What is the unit of current? Current unit is ampere. And what is ampere? Ampere is coulomb per second. Ampere is coulomb per second because after all, I is equal to Q by T. Therefore, it is coulomb per second. So we are just going to use this concept and get what is current. Okay, so current is going to be charge is E, Q is E, 1.6 into 10 to the power of minus 19. And I have to write T. So what is T? T is F. A time taken for one rotation. Reciprocal is frequency. So let's just put that. Okay. So you will again see that the unit is coulomb per second. Coulomb hertz or coulomb per second. So that's how you get your current. So do this here. 1.6 into 10 to the power of minus 19. Frequency is 6.6 into 10 to the power of 15. Substitute it here. You're getting your current in amperes. So one single electron going around in a circle, because the circle is very small and because the frequency is high, look at the current. It is milliamp current. Milliamp current. Normally, for you to get a milliamp current in a wire, 10 to the power of 28 electrons should have been moving. Whereas here you see a single electron is able to create a current of 1 milliamp. Okay, so now put that into the equation and look at the value of the magnetic field you're getting. It's an appreciable value. It is 12.6 Tesla. 12.6 Tesla is an appreciably big value of magnetic field. So now I hope you're able to understand that a single electron can also set up its own magnetic field. So this is a hydrogen atom. You have only one electron. Similarly, you can talk about other atoms where many electrons are there. The electrons may not always be in one orbit. They may be in different orbitals, but then all of them produce their own magnetic field. And magnetic field is a vector. You can add up all these vectors and talk about a magnetic field associated with a given atom. Okay, in the next class, what we'll do is we'll look at what happens instead of, we have seen one wire, we have seen the magnetic field it can set up. Next, what we are going to do is we're going to take two wires, two parallel current carrying wires, and see what is the resultant magnetic field at a point. Basically, we are going to use the principle of superposition to find out the net magnetic field because of two wires carrying currents. Okay, so I stop here. If there's something to ask, you can ask. Anything? I know with an exam tomorrow, hardly anyone is going to be in a mood to ask anything. So I also don't feel it even right to ask you if you have something to tell me. Anyway, follow whatever I have done here. Just save, the recording is going to be made available. Please go through that. And if you still have any doubt, you can always come back to me. I can answer your doubt. Tomorrow you have an exam. Anything you want to ask? A couple of minutes we can spend if you want to ask something. Nothing. Well then, looks like everybody is totally properly prepared. So there's no doubt also. So I'm stopping the record. All the best for tomorrow's test.